Okay, grade 11 chemistry. This is video number 3. It's about ionic compounds, simple ionic compounds specifically. You would have probably seen this already in grade 9, but since that might have been a while ago for some of you, we're going to do a quick recap of ions, how to predict ions, and so on. So here's what we're interested in doing today. It's a shorter kind of schedule than normal, so we'll probably spend some time doing practice questions at the end of the video. What we want to do here, we're going to predict the charge on an ion and do some naming of just individual ions. Then we're going to name simple ionic compounds after we've learned how to name the actual ions. And then we're going to do the slightly more difficult thing of turning a name back into a formula. But thankfully, we always have our handy-dandy periodic table to help us out. Jumping into it, first with predicting and naming ions. Ions are charged atoms, and these atoms can only get charged when they gain or lose electrons. So it has to gain or lose electrons, because if it gained or lost protons, which is the only other way it could gain or lose charge, it would become a different element, right? Carbon always has 6 protons. If we change the proton number, it's going to turn into nitrogen, or boron, or whatever it would turn into. So ions have to gain or lose electrons, and we have this rule called the octet rule, that says that ions try to be like the nearest noble gas to them. And when we talk about the nearest noble gas, it's helpful to remember that the periodic table, wraps around itself, right? It wraps around itself and down by 1. So when we get all the way to the end of the table and get to, say, neon, right? Neon here. Neon is number 10 and sodium's number 11. So you can think about the table as almost like a periodic cylinder at that point, where the sodium is going to come after the neon in the table like that. So nearest doesn't necessarily mean physically nearest as in on the sheet of paper. The nearest noble gas to sodium is actually way up here. That's neon, right? Sodium is very close to neon. It's only 1 electron away from being neon. This is why we say metals tend to lose electrons, which are these guys on this side of the table, and nonmetals tend to gain. So metals tend to lose electrons, nonmetals tend to gain electrons. And we have this line called the zigzag line or the staircase line that kind of separates the metals from the nonmetals. Along the staircase line, we have these things called the metalloids, which are kind of like metal-y-ish, right? So like silicon can kind of gain or lose depending on what's going on with it. So can germanium and antimony and tellurium and arsenic and stuff like that. Carbon is also a bit iffy, but a little bit harder to make it act like a metal compared to a non-metal. These are all the metals, these are the non-metals, and then we have our Lewis groups 1, 2, 3, 4, 5, 6, 7, and 0. And that's from up here. If you remember the Lewis groups, it actually makes it very easy to predict what kind of ions they're going to make. So one way to do this, to predict it, is to see how close they are to noble gases. Fluorine, for example, right next to neon, it'll gain 1 electron, become negatively charged, become fluorine minus oxygen. 2 away will want to gain 2 electrons to get its octet. So 1, 2, so it'll be a charge of -2. Nitrogen will make a charge of -3, carbon -4. Boron actually goes the other way, acts like a metal. You can make non-metal compounds with boron as well. And then same thing on this side here. Lithium, 1 away from a noble gas, and sodium, potassium, 1 away from a noble gas. Remember that it wraps around to the other side. So they'll all make +1 because they will lose their electron. They tend to lose their electron. You might have heard in previous classes that they want to lose electrons. That is just blatantly false. They just have a very weak hold on their electrons, if you remember our discussion of ionization energy from the last video. Same thing here, group 2 will typically make a charge of +2 because they want to lose 2 electrons. So on this side, typically the group number, right, +1, +2, +3 most of the time. But there's an even better rule, and the even better rule is to talk about the unpaired electrons, the number of unpaired electrons. If you remember back in the Lewis diagram lecture, we spread them out until there's 4, and then after there's 4, we start pairing them up. And so an unpaired electron doesn't have a buddy. Electrons that are paired don't want to bond. Electrons that are unpaired do want to bond. So nitrogen has these 3 unpaired electrons. That means there's room for 3 electrons to join them. 1, 2, 3. So it'll make a charge of -3. It wants to pull in 3 electrons from somewhere else. Magnesium has 2 electrons. They're both unpaired, so it's probably going to make a charge of 2. Aluminum has 3 unpaired electrons. It'll make a charge of 3. 3 plus in that case. 2 plus for magnesium. Only 1 unpaired electron for chlorine. It'll make a charge of -1. 4 for silicon means +4 or -4 are kind of equally likely. Silicon's an interesting case. Right. Now, in terms of ionic bonds, what happens is that a nonmetal will steal electrons from a metal. This is straight up down to electronegativity. Chlorine has a very high electronegativity. It's a smaller atom and has more positive charges in the center, so it has a much stronger pull for outside electrons than sodium does. Chlorine's attraction breaks the first ionization energy of sodium, which is quite low, and pulls the electron over. This results in an energy release, and it's a spontaneous reaction. Interestingly, after the reaction, you get the sodium ion and the chloride ion. The sodium ion now becomes very small because it's down to 2 shells and a pretty good effective nuclear charge, whereas the chloride ion actually gets bigger because now there's more shielding. So the chloride ion gets a little bit bigger, but the sodium ion gets markedly smaller. So this started smaller than the sodium. This was smaller than the sodium, but when they actually become ions, the chloride ion becomes bigger than the sodium cation, which is neat. In terms of naming, right, because it's not just predicting ions, we can predict the charge using our unpaired electron rule. Naming ions is the next piece here, so take away that. In terms of naming ions, there's some terminology here. The positive ion is a cation. The stupid way to remember it is that cat ions are positive. Cats have pos. Cations are positive, and anions are negative. So chloride anion is negative. And a rule came out, or a rule developed very quickly to distinguish cations from anions with a simple piece of terminology, and that's this "ide" ending, I-D-E, "ide" ending. So the positive ions just keep their name. The negative ions get this I-D-E ending. There is, however, a common misconception here that I want to address. So I'm going to go over to the document camera. Here's the document camera. And I guess I should probably turn on... Yeah, there we go. There I am. And I should turn on the current topic. Naming ions. And we're going to talk about this "ide" ending. The "ide" ending is only for single atom ions. Only for single atom ions. What do I mean by that? Well, let's look at nitrogen here. Right, nitrogen has a valence of 5. I got that from the table. And when I look at the table, here's nitrogen in group 15. So, valence of 5. If we use our unpaired electron rule, it's got these 1, 2, 3 unpaired electrons. So we predict that this is going to make this ion, a nitrogen with a charge of 3-. We're going to call that ion. It's an anion because it's a negative ion. It's an anion. It's going to get this "ide" ending. So this is called nitride. It's called nitride. An incredibly common error that I see in grade 11 chemistry. And I think I've already asked this in class before, and you guys made the error that I expected you to make, is that people like to call this nitrate because they remember this stuff called nitrate and it had nitrogen in it and it was important. Well, that's not nitrate, right? This is nitride. We use that "ide" ending very, 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 very specifically for single atom ions. Nitrate is a polyatomic ion. It's this little block and it has a charge of -1. That's nitrate. There's also nitrite, NO2 minus. So there's these different ones that have nitrogen as a central atom, but only this one is a single atom ion. Only this one is an ion that came from a single atom, and that's why it gets the "ide" ending. You get the same thing often enough with something like sulfide, right? What is sulfide? And a lot of people will say it's SO4, 2 minus, which it isn't. Right? It has to be a single atom. So sulfide, because it's an IDE, it must only be sulfur. Only sulfur, just one sulfur, that's it. That's what the "ide" ending tells us as chemists. When we look at sulfur here it is, sulfur, group 16, 2 away from krypton, or 2 away from argon, and that means that it would have a charge of -2. You can write -2 or you can write 2 minus. It's up to you. Chloride, usually Cl minus. We don't write the 1. It's kind of a math thing. So this is chloride. So that's the sulfide ion. That's the chloride ion. The "ide" is always a negative and always a single atom negative. The single atom thing is very, very important here. In terms of positives, there's no special name for them. We just call it, like magnesium ion. Right? If I say magnesium ion, you know that it's magnesium. And as far as a charge goes, we go to our table. Here's magnesium in the second row, row number 2. That's 2 valence electrons. It will have a charge of +2. That's magnesium, 2 plus. So that's our review of predicting and naming ions. Magnesium ion versus, say, the fluoride, right? Fluoride ion. There's that "ide" ending because it's a single atom negative ion. So that's our first section done, right? It's we've done our learning goal of predicting the charge on an ion and then naming ions. We're going to move on to naming simple ionic compounds, so I'm going to pause and get into naming simple ionic compounds. Okay, so the next section here is naming simple ionic compounds. And the keep in mind is very, very handy. It's extremely difficult to get a single atom of something. There are, for example, quintillions of atoms in a grain of salt. That is a 1 with 18 zeros after it. Right? It's a billion. That's how many in a single grain of salt. And what if I chop up that grain of salt really small? Well, even if you cut it in half, now you have half of a quintillion. That's a 5 with 17 zeros after it. It's extremely difficult. So in any reaction, in any kind of experiment, you're going to have billions upon billions upon billions of atoms. So these things are going to combine in ratios, numbering in the quadrillions and the quintillions. So that's important to realize, because it's not like we just have one magnesium and one fluorine. We have billions of magnesiums and billions of fluorines all over the place when they're going to react and when they're going to do, this kind of thing, when they steal. So it's never just one. There are billions. That's something to keep in mind. So how are these going to combine? Well, you've got your magnesium on the one side, and there's a charge of +2 there. And on the other side, you've got a fluorine charge of -1. That means that the magnesium, right, must have given up one of its valence electrons to fluorine. Right, the magnesium must have given one up to a fluorine, but it still has this other one, and now this fluorine is full. It's got its full octet. So where does the other one go? Well, it must go to somewhere else. There will be, as I said, there are billions of these things. Billions and billions of these things. So what's going to happen is the second electron is going to go to a different fluorine. A different fluorine. So what you're going to end up with is one magnesium and two fluorines. One magnesium and two fluorines. And so it's going to be, a magnesium and two fluorines. So we could maybe draw it like this. But that seems annoying. We don't want to put those little pluses in there because everybody already knows, we've got a periodic table. We know that magnesium is going to make a 2+. We know that fluorine is going to make a minus. So instead, what chemists came up with was this notation, MgF2, which is the same as that notation, right? It's two fluorines, because there's two of them, and one magnesium. So MgF2. MgF2. In order to name it, we simply use the names of the ions. This is magnesium and fluorine together. Specifically fluoride, right? It's the ide ion, the fluoride ion. So this is then called magnesium fluoride. Magnesium fluoride. I love fluoride compounds because my students often say fluoride. They put OU instead of UO. So I'm always on the lookout for people writing fluoride instead of fluoride. It's just kind of a funny thing that happens. Okay, that's magnesium fluoride. Relatively simple to understand. You might have heard of the crisscross method. It works pretty well. So let's talk about the crisscross method. The crisscross method says something like this. Let's say I had something like sodium and oxygen that are going to react. And then I look at my table. Sodium's over here in group 1, so it's going to make a 1+. +1. We usually don't write the 1, so we can just write plus. Right, Na+. Oxygen's over here, 2 away from neon, or group 16. It's going to make a 2-. And then the crisscross method says you just cross over the numbers. So this becomes a 2 because that's a 2, and we take that 2. That becomes that 2. This is a +1, which becomes a 1. So it predicts Na2O. Na2O as our simplest ratio. And indeed, that is what we see. Right? If we do the whole Lewis diagram here, right? Oxygen has these 2 places for electrons, and it's just going to steal those from one sodium here. Right? It's going to steal it from one sodium here and from another sodium there, and so you get Na2O, and then the sodiums both lose their outer shells, and the oxygen gets a full octet, and it's happy. So this is predictive. The reason that it's predictive, the reason that the crisscross method works is it's literally cross multiplication, like in math, is because 1 times 2 is equal to 2 times 1. And we want to balance the charges. So you can do the same thing by just going, well, I have sodium and I have oxygen. I have too much negatives, so let me add another sodium. And there's my 2 sodiums and my 1 oxygen, so that's Na2O. So that's why the crisscross method works, because 1 times 2 is equal to 2 times 1. Right? Here the crisscross is actually crisscrossing the factors of our common denominator. But do be careful of the crisscross method, because there are certain cases where it doesn't quite work right. And those cases are something like this, like titanium, which can make a 4+, and oxygen, which is a 2-. If you try to crisscross this suggests that you have titanium 2O4, because right here you're crisscrossing. The 4 goes here, and the 2 goes here. But that's not the simplest ratio, right? That's not the simplest ratio. The reason that we want the simplest ratio is that even this isn't true, right? It's not Ti2O4. It's like Ti, 6 billion and O12 billion. There's twice as much oxygen as titanium, but it's in the quadrillions. It's in the sextillions. We don't know. So we want the simplest ratio because we're just interested in the simplest ratio. So Ti2O4, actually it's going to be TiO2. And if we diagram that, that's because the titanium, which we know has 4, right? It's going because it's going to lose 4. Each oxygen can just take 2 of them. And each oxygen can just take 2. So you can end up like that. Or another way to diagram it without the Lewis diagrams might be to just start with titanium 4 plus, oxygen 2 minus, and then you're going, oh, well, I don't have enough negative charges to make it equal, so just do another 2 minus, and then that's 4 plus, and that's also 4 plus. So TiO2, it's TiO2 is what we predict for this ionic compound. So that's how we predict and name these ionic compounds. I'll do one more just because I like this one. Let's take aluminum and nitrogen. And when we look at aluminum, group 13, on this side of the zigzag line, so it's going to make a 3 plus. Nitrogen, group 15, 3 away from neon, that's a 3 minus. Okay. What kind of compound is it going to make? Well, 3 plus and 3 minus are both 3, so we're good. We're even. So this will just make aluminum and nitrogen like that. 1 aluminum, 1 nitrogen. What do we call it? What do we name it? Well, aluminum as an ion is just called aluminum ion. Aluminum. Or aluminium, if you prefer. And nitrogen as an ion is called nitride. Remember, nitride. And the amount of people that try to tell me that this is aluminum nitrate is way too high. So that's aluminum nitride. That's simple naming of ionic compounds. So that's naming. That's naming over with. The last piece here is turning a name into a formula. So it's easy to turn a formula into a name when you have a simple ionic compound, because it's literally just aluminum and then "ide" for this guy because it's a single substance, a single atom. The hardest part is just separating it. Aluminum nitride. But turning a formula, turning a name back into a formula is the harder part. So I'm going to pause and do my setup, and then I'll talk about turning names back into formulas. Okay, so the last piece here is going from the name to the formula. By that I mean, let's say I had sodium phosphide. Right, sodium phosphide. When I look at this name in my head, what I see is, okay, well, I've got an ionic compound. I know it's ionic because there's this "ide" ending on the phosphide. I know that this "ide" ending is only used for single element anions, so that must be just P. Just P. And if that's ionic, that's an ion too, so the sodium ion is Na. Then I think in my head, what are the charges of sodium and phosphide? And charges first. If you look up at the keep in mind charges first. So sodium being in the first row, charge of +1, Na plus. Phosphorus being in the 15th row here under nitrogen, 1, 2, 3 away from argon, so it's going to make a charge of 3 minus. And then the way I think of it in my head is we've got 3 sodiums, because those 3 pluses have to match this 3 minus for the phosphate, 3 minus for the phosphate. Therefore, this thing has a Na3P. Na3P. So that's the formula. Sodium phosphide's formula is Na3P. If you prefer using crisscross, that's fine too. Just keep in mind that exception, right? The plus would come over here, and the 3 would come over here. So this is a 1, and that's a 3. So you end up with the same thing, Na3P. And that would be the formula from the name. Let's try a few more just to get the hang of it. Let's talk about my favorite ionic compound, aluminum oxide. aluminum oxide. You know what, that should be a lowercase a. This is something else. Names are always lowercase unless they're at the start of a sentence. So IUPAC, the people that make the rules, say that all chemical names should be lowercase. So you see them uppercase somewhere, someone doesn't know the rules. So aluminum oxide, once again we have this split between the aluminum and the oxide. The "ide" tells me that it's just a single oxygen. That means this is also ionic, aluminum. And then I go to my table to figure out what the charges are. Aluminum is in group 13, 3 away from neon, 1, 2, 3. So 3 plus. Oxide is over here, 2 away from neon, 1, 2. So 2 minus. And then here you can just crisscross, right? Al3O2. Or you can do it the way that I always think about it, which is I need 2 aluminums and I need 3 oxygens, because that makes excuse me, that makes 6, and that makes 6 minus. So I have 2 of these and 3 of these, so that makes it Al2 because there's 2 aluminums, and O3, 3 oxygens. And of course you could always just have yourself a crisscross. Right, Al2, O3. Right, crisscross those numbers. Right, just one last one here, and then we'll finish off this super quick video with a look forward to the slightly more complicated stuff. Right, so one last one. Let's try something sneaky. Let's try calcium sulfide. Right, calcium sulfide. What would the formula be? Well, you got calcium and sulfide. The "ide" tells me that it's a single atom, right? "Ide" is only for single atoms. You can think like individual, right? "Ide," I don't know, ID, maybe, "ide." Sulfur, S. This is calcium, so it's calcium. I look at my table. Sulfur is over here, 2 away from argon. The 2 minus. Calcium is over here in the second row. That's 2 plus. And then of course crisscross would lead you astray here, right? It would be a 2 and a 2. But it's not Ca2S2. It is not that. It is simply Ca2S. Ca2S. Right? Sorry, CAS. CAS. That's it. CAS. Because you just need 1 and 1 because that equals out the charges. So that's going from name to formula. Just one quick detour into what's coming next, which is going to be more complicated ionic compounds. So we're going to talk about compounds like FeO and Fe2O3, both of which are perfectly acceptable compounds because this is iron in a 2 plus state and this is iron in a 3 plus state. Now the oxygen is not going to change, it always makes a 2 minus, but because of the way it works, this is just 1 to 1, whereas this one we need 3 of these to match our 2 of these. It's a slightly more complicated compound because there's 2 possibilities for the iron. So this is iron 2 oxide and this is iron 3 oxide. We have a slight difference to the name. So that's coming tomorrow. Also coming tomorrow are the dreaded polyatomic ions. So we're going to talk about, nitrate versus nitrite, sulfate versus sulfite, things like that. The worst it can get would be like, I'll give you iron 2 hydrogen carbonate. And you have to give me the formula of iron 2 hydrogen carbonate. But the same rules apply. You just have to figure out where the division is. And in this case, the division is there. Iron, and then the hydrogen carbonate. And then it's iron 2, so that's Fe2 plus. Hydrogen carbonate is HCO3 minus. And then you need 2 of them. to equalize the charge. So you've got one iron and you've got two of these guys. Right, two of these guys to equalize the charge, and so you end up with FeHCO3 2 as the formula. But that's what we're going to get to with tutorials and stuff tomorrow. For now, this video is over. That was a quick one, only 30 minutes. Thanks a lot, and I'll see you guys in class for this stuff.